Hi everyone, so today we're going to talk about the logistic equation, but first I'm actually going to talk about an exponential graph, an exponential model, for if we wanted to model the spread of COVID-19 actually. So there's a lot of models that came out at the beginning of the pandemic and that have been kind of evolving ever since that help hospitals prepare for when they should expect a certain number of people or how many beds or how quickly it'll spread, that kind of thing. And they're kind of ever evolving, but there are a couple different models. And at the beginning, you might have heard people saying that the virus was spreading exponentially, right? And we know what that looks like. It looks kind of like that, right? Where this would be like day 0, I guess. This is like time, and this is number of cases. Right, so like let's say in the US, let's do it at Nobles, for example. So let's say nobody at Nobles to start with has COVID-19. And let's say one person, so at time equals 0, we have one case, one person goes to some social event with students from a different school, gets COVID, doesn't have any symptoms, feels fine, goes to school. And let's say we didn't have our protective measures in place. We were wearing a mask. It was spreading as rapidly as it's spreading other places. So let's say it's actually doubling. That's how you spell that? Doubling every day. So we're doubling our cases every day, right? So we start with 1, we're doubling every day. So if we want to set up an equation for this, right, we can have our COVID as a function of time, or cases as a function of time. Actually, both start with C. We have one initial case, right? We're doubling every day, and we'll have T as time in days. Right? So now we can kind of say, like, let's say on the 5th day, how many people would have it, right? So then we have cases as a function of time. On the 5th day, we'd have 1 times 2 to the 5th, which is, 32? So this would be 32 cases. And we can keep going, right? But what's actually different, so this is an exponential model, right? But what actually happens, right, is we start with our case and we increase, and then we're actually going to get to a flattening off point, right? So this is like negative time, so it doesn't really matter, but right, there's only so many people that work at Nobles or go to Nobles or are at Nobles, right? There's only so many people that are here, right? We have a maximum capacity, right? It won't go forever, right? There has to be a boundary. There's only 650 students plus about 200 faculty and staff, about 850 total. Let's round it up to 900, for example. 900 people maximum, right? So this is where the logistic equation comes in, a logistic model. So the first one that I drew in white that we've been talking about so far is an exponential. It just grows exponentially and keeps going. There's no boundary, there's no limit. But in real life, right, there is a boundary. There is a limit. There is going to be this kind of leveling off point, right? We're going exponentially, and then we get to what's called an inflection point, which would be this kind of like point where it stops going like faster and faster, and now it's still increasing, but at a slower rate. Our acceleration has slowed down. And so we have this exponential kind of curve here, and then it flattens off. Maybe I should have drawn this on a closer model, but same thing. So it has the same exponential kind of shape, and then it levels off as we get closer and closer to our upper horizontal asymptote. So for a logistic equation, we actually have 2 horizontal asymptotes. We have one at 0, basically our minimum, 0 cases, and then one at our maximum. So what does this equation look like? This equation looks like, we can call it L for logistic. And remember, actually, it's logistic, not logarithmic. Those are 2 different things. So we've been doing logs in class that are the inverses of exponentials. And logistic, though, both start with LOG, are not called logs and are totally different. So we have L of t as a logistic equation as a function of time. And this would be our maximum or our carrying capacity, or like that upper horizontal asymptote actually goes on top, divided by 1 plus a, which is just constant, e to the negative k t. T is our variable. So our m up here is our carrying capacity. Carrying capacity, which is like our maximum, right? The total number of people in our population, the most people that can get sick, the most, like, the maximum amount of like wolves that could live in our national park if we introduce like a couple wolves to start or something like that. So this is gonna be our maximum like horizontal asymptote. And this is actually because this is kind of cool, because if we have the limit as t approaches infinity, as t is getting bigger and bigger and bigger and bigger, right, then we have m over 1 plus a e to the negative k basically times infinity, and k is always going to be a positive constant, and the negative means that if k is always positive, then the negative k means this will always be negative, basically. So that's because then at the limit as t approaches infinity of this function, right, we're going to have m over 1 plus a over e to the k times like infinity, or to the kt, and we're doing the limit as t approaches infinity. So we have basically a huge number in that denominator of the denominator, which is going to make a over a ginormous number. A over infinity is basically 0, right? That whole thing basically goes to 0. So the limit as t approaches infinity is just going to be m over 1, or m. And then we also can do it the other way, right? What's our minimum? What's our lower horizontal asymptote? Usually it's 0, but it's as t is approaching negative infinity. So if we have the limit as t approaches negative infinity of our L of t, right, we're going to have m over 1 plus a e to the negative k times t, or the negative k times negative infinity, basically. Sorry, make this a little smaller. So then we're going to have m over 1 plus ae to the negative times a negative, or like e to the k times infinity, basically, aka ae to the k times infinity, which is, again, huge number. Big number. Right, so now again we basically have a number divided by an infinitely large number, so this whole thing comes out to 0. And that kind of makes sense, because it's like, what's the minimum amount of people who can be sick or who can live somewhere or whatever is 0. Other things, the function also, we can figure out our initial amount, right? If you plug 0 in for t, it'll depend on what a is. A is also a constant. So we'd have to have, but like L of 0, right, is going to be m over 1 plus a e to the negative k times 0. Well, e to the negative k times 0 is just e to the 0, right? And e to the 0 is 1. So now we're going to have m over 1 plus a. So that will be your initial amount, right? Depending on what m and a are, right? You can find that number. So this is your initial, like, amount of people who were infected, or initial just like amount of people or wolves or whatever. So for our one that we started with at the beginning of this, we can think about, okay, so if we have cases at nobles, right? We have cases as a function of time, and we said 900 was our maximum, right? So we can put that in the numerator. Then we have 1 plus, we don't know what a is, we don't know what e is, or sorry, we know what e is, we don't know what k is, and t is our variable, right? But we know that I said that we started with one person, right? So our initial amount when t equals 0, we had one case. So we can say 1 equals 900 over 1 plus a, right? So then a has to be, what, 899? Okay, so now we have 2 bits, right? So now we have c of t is 900 over 1 plus 899 e to the negative kt. And now, in order to solve for k, to finalize our equation for our logistic growth of COVID cases at Nobles, we'd have to have another point, right? So let's do that. Scroll. We'd have to have another point on our graph. So like after 2 days, what was it? And if we say that it's still like after a couple days it's doubling, like we're still in our exponential growth phase. Let's say like at t equals let's say after t equals, even if it doubles like the next day, so t equals 2, right? We have 2 cases. Now we can solve for what k would be. So we have c of 2. Oh, sorry. Actually, I want to erase that. Make that equal to 2. Pick too small of a tip there. 2 equals 900 over 1 plus 899 e to the negative k times 2. Right, and we'll need a calculator to solve this as well, because then we'll have 900 over 1 plus, this is really not that simple, e to the negative 2k, basically. And now we can kind of start to solve, right? We can say 2 times just multiplying this denominator by 2, right? Like imagine this step isn't here. Multiply this denominator by 2 to get this on the other side. So I'll have 2 times 1 plus 899 e to the negative 2k, right, equals 900. I can divide by 2. 1 plus 899 e to the negative 2k equals 450. Sorry, this is getting mini. Subtract 1, 899 e to the negative 2k equals 449. Divide by, this is 899. Divide by 899, I don't know what that is off the top of my head. 449 over 899. And then now, right, in order to solve this, for k, I need to use a logarithm, right? So I have ln of 449 over 899 is going to equal negative 2k. Divide that whole thing by negative 2. K equals ln of 449 over 899 over negative 2. And then whatever that number comes out to be, I'm not prepared. I do not have a graphing calculator on me right now. We would plug that back in to our equation right here. And that would be our logistic equation that's modeling our growth, right? So this is a little bit more realistic for modeling the spread of COVID over a period of time, because we have an actual carrying capacity. It's actually going to slow down as we approach that carrying capacity, and the shape of the graph of a logistic curve kind of accounts for that, right? So it kind of looks like that. And so this would be at 900, right? And so this is the 0.01, and we'd have 2 2s on there. And so then this actually is like we have a really quick spread at the beginning. It's getting faster and faster and faster. And then after we get to our inflection point, this turning point, we're still increasing. We're still like more people and more people are getting sick. This is like, this is all theoretical, but what we're slowing down as we get closer and closer to our carrying capacity, which is a little bit more of a realistic way to model growth in like nature or in communities. So I got a graphing calculator, and I found that K in the last problem, or in the problem we've been doing, is going to be 0.347 roughly, which is good because it's a positive number. That's a good sign. We're on the right track. So now I can put my final equation together, right? I have cases of function of time was 900 divided by 1 plus 899 e to the negative 0.347 t, right? So now I can say, like, how long is it going to take, right? What time, how long is it going to take for us to, it can't actually reach 900 technically, based on this model, because it's an asymptote, so we'll never actually get there. But, like, let's say I wanted to say, like, how long will it take for us to get to half, right? How long, if we start with one person has COVID from going to a party and then comes back to school, and this model is correct, like it was growing at this rate, right? How long does it take for us to get half of our school population, right, infected? Oops. We can also ask how long, after, let's say, 10 days. Actually, let's go let's go 10 days. So after 10 days, right, how many people have gotten COVID? Right, so two different applications of this. This is just a modeling example. So try these. I'll do the solutions on the next page. So for how long does it take for us to reach 450, right? I'm just going to solve for t, right? 450 equals 900 over 1 plus 899 e to the negative 0.347. Come on. T, right? So I just need to solve for t. So I'm going to just say this is 1 plus 899 e to the negative 0.347 t equals 900 divided by 450, or 2. Then I'm going to subtract 1, divide by 899. I'm going to have e equals negative 0.347 t equals 1 over 899. Right? So this is a t, not a plus sign. And now I need to use logs, right? So ln of 1 over 899. I'm going to skip a step. All divided by negative 0.347. It's going to equal my t. Let's put that in my graphing calculator. Ln of 1 over 899 divided by negative 0.347. 19.6 days. It's not very long. And then the next one, right, was how many people have been infected after 10 days? We can really just plug this in. Again, we're going to need to use our calculator. So the key part in your calculator is making sure you have all this stuff in parentheses, because otherwise if you do 900 divided by 1 plus whatever, it'll just do 900 divided by 1 and then plus the rest of it, like in the numerator. So make sure you have parentheses. This one, there's less solving. You don't need to use logs. You're literally just plugging in 10. So we're going to actually have, I'll write a couple steps out. We have 900 over 1 plus 899. And then we have e to the negative 3.47, or I'll just do that in my calculator. E to negative 3.47 is 0.0311 and some other digits. I'm just going to leave it in my calculator, not round, and just multiply that, like, so answer times, so just like if you have the thing prior and then you just hit a multiplication or division or whatever function. At the beginning of the next line, it'll do ands the previous answer times whatever you're doing. So answer times 899, and then plus 1. So I have now 900 over 28.97. 900 divided by, answer is above the negative sign all the way down the bottom, second negative. So I got 31.06 after 10 days, about 31 people, right, now have COVID. Yeah, so this is also, people use models like this to model the spread of COVID, and in the US, actually, it's kind of like piece where it's still rising, still like on that positive upward trend in the logistic curve. It was actually doubling every day, so I kind of took that from that data that I found. I can share a link of that website that I found. It was from November, so it's a little bit old, but that was just the inspo. Okay, that was fun.